I'd like to introduce Mick Jordan from Sun Labs. He received his PhD at Cambridge and worked on Modula 3 and is now ready to bless us with a talk about his current project, which is Project GuestVM, which is a Java platform implemented in Java and hosted on Xen, something which is very interesting to Googlers in general, I think. And so here he is, Mick Jordan.
Thank you. So I hope you can hear me okay. I'm not used to sitting down while talking, so it's going to be interesting. I will stay in my seat, because that will prevent me from trying to walk across the screen and lose the mic. So Project GuestVM, an extraordinary generic name. It might be Project Guest JVM, but we're not allowed to do that in Sun unless we pass the TCK test. So it used to be called Java Guest, which I really liked, but I can't use that either. Okay, so here's the outline of the talk. We can talk about the context in which this work takes place, why it makes sense to do it, and some of the issues that we're trying to address, the opportunity that we have at the moment, and with various pieces coming together, and the actual goals of the project. Then a little bit of related work. I'll talk about Xen and Maxine. Maxine is a new JVM at Sun Labs that I'm making extensive use of. Then quite a bit about the details about the GuestVM itself, future work, and then conclusions to date. Now you'll notice in there are no performance measurements. And how can you give a research talk without performance measurements? And I agree that's bad. Basically, this talk's a little premature. I would have preferred to have done this, say, in 6 months' time. But I don't know where the world will be in 6 months' time. I decided sort of last fall when Sun announced its big layoffs and when things were going down the tubes that I would get out early in 2009 and talk about this work, regardless of the actual state. So that's why I'm here today. So the context. So Java's been around for 14 years, I believe. And over that time, it's evolved in God knows how many directions, and just about every direction. And it's pretty much a complete platform now, for server-side applications, certainly. There really isn't anything that you can't do in the platform, either with the platform itself or with libraries from third parties. Modern Java applications don't tend to contain native code now. I mean, they used to have native code partly for performance reasons and partly to plug holes in the platform, and both of those have essentially gone away. So most server-side apps are actually now pure Java. The third bullet's kind of a little bit more perhaps contentious, but I think that generally speaking, the later you do your compilation, the more analysis you have about what's really happening in your application is about what you think might happen in your application when you compile it statically, you're going to get better results. So we would like to use that runtime compiler as much as we possibly can. And the final bullet is hypervisors are really becoming ubiquitous. I think perhaps they're not now, but within a few years, I think every single server machine, possibly every desktop, possibly even every cell phone will be running a hypervisor. It's not clear which hypervisor it'll be. There's competition there. But they will be there, and they will be you can just assume they are there. So some of the issues with the Java platform as it is implemented today. I mean, typically, a Java platform is implemented with a JVM that's written in C code or C++, and a mixture of Java code for the libraries and native code, some of which is necessary in order to just deal with that fact that that API layer in the OS is written in C, and you have to have some way to connect to it. The end result of this is a fairly complicated development and debugging environment for platform developers. But perhaps what I'm more interested in is that crossing the layers that you have to do as you go from Java into C code into the OS can be expensive. And if that's what you're spending almost all your time doing, then that's an issue. And certainly server apps spend the vast majority of their time traversing up and down the network stack because they're either talking HTTP input from somebody, from a client, or they're talking JDBC output to a database on the backside. So it's all layer crossing constantly down into this layer that was not designed with Java in mind. Furthermore, the dynamic compiler that I just said good things about doesn't see any of these layers. It sits above that, just doesn't look into them. Essentially, the code you got from the C compiler is what you get. And as you know, the Java platform also has some special needs. It has automatic storage management or garbage collection. It has threading as part of the language. And those things are not well served by existing OS APIs that were designed in, the 70s for the most part, and really not, are really trying to support C and not a language like Java. Now, various people have tried to address this with Java operating systems, Java on the bare metal, the real bare metal. The problem with that is it's really a lot of work. And it's a lot of ongoing work in the sense that network cards keep changing. The amount of work you have to do is prohibitive, essentially. You just can't really approach it. So the opportunity that we have, particularly with Xen, Xen has a para-virtualization API, which means that it provides a somewhat higher level API than the bare metal. In particular in respect to I/O. I'll say a bit more about that later. But what it does is it dramatically reduces the barrier to entry for a quotes bare metal JVM. It's just a lot less work to do, and you only get to do it once. If you really want to do a lazy approach to this, in fact, you can even sort of delegate almost all the I/O that you want to do, because in a hypervised environment, you have a sibling operating system potentially running by your side, which has full I/O capabilities. So you can just simply delegate network or file I/O off to that sibling guest and don't do any of that. And that's how I got started, and that's how a number of other projects have done that. The final piece in the opportunity is that we have this new research VM being developed in Sun Labs. It's a research JVM. It's written in Java 5, or these days we sit on 6, but it's written in Java. So we have the potential here, the fundamental basis, the core of the system is now written in Java. So we have what we need to get towards an all Java stack. So this is the main research question of the project, really, is can an all Java software stack outperform this traditional layered approach? And there are some metrics that we can use for this. First and foremost is always runtime performance. People always want things to go fast, and that's certainly in the Java world has been a constant Achilles heel. A lot of people I talk to, though, are perhaps more concerned about ease of management. It's actually easier to manage an application that is running on this platform than it is one that's running on an OS, because everything you could possibly configure is now configured through Java properties, essentially, through the standard Java mechanisms. So if you want to mess with the network stack properties, you do it in that way. You don't have to have two different mechanisms, two different things to talk to. And putting together an application is simpler because you don't have to configure an operating system first and then the applications on top of it, shell scripts to run the thing, and all of that stuff just goes away. Finally, as I alluded to, platform developer productivity. We can hopefully improve the lot of the typical platform developer who now gets to use integrated development environments like NetBeans or Eclipse, and perhaps can say goodbye to Make and VI once and for all. Okay, so the goals of the project, really. First and foremost, I want to enable optimize, possibly specialized server-side applications with an all Java software stack. It is an application play. I'm really not making an operating system. I'm not interested in an operating system. I've been there, done that. We did think about doing that. The previous project I worked on, actually with Greg Tchaikovsky, who I see is probably in the maternity ward, not here, was actually virtualizing the virtual machine where we could run multiple applications on a single VM, and we did think about putting that on top of Xen and going further down that road, but in the end backed off to a single application play. So we're looking at applications like application servers, game servers, and so on, and not trying to boil the ocean. We want to exploit access to the low-level mechanisms we get with the hypervisor, and particularly for thread scheduling and memory management. We get much lower-level access in the hypervisor environment than we do in the OS environment to those features. The last two I alluded to before, really simplifying development of apps and increasing productivity. These are essentially, I would say, in order, with priority starting at the top. So here's what a stack looks like in the conventional world on the left and in the GuestVM world on the right. Everything in shades of yellow is C code or C++ code, except the hypervisor, which is also C or assembler right at the bottom. And you notice I assume that we have the hypervisor there. It's ubiquitous. So everything's running on the hypervisor, and that's the base of everything. So on the left-hand side, we have the JVM written in C or C++, some part of the platform library is written in C. We have a C library, and we have an operating system layer. And in terms of footprint, of course, the size of those boxes is wrong. I mean, the OS is a much bigger piece than it appears in the picture. But then I couldn't fit the name in if I did it that way. On the right, we have the GuestVM world. The only piece of C code we have is a small microkernel, which it's more of a Xen layer or a hypervisor interface layer than a microkernel per se, but it has facilities like the base of threading and so on is done at that layer. So it is really a microkernel in that sense. And then we have a network stack and file system access above that. And then we have the platform libraries that were previously written in C. The parts of the platform libraries that were in C are now in Java. And we have the Maxine JVM, which is also in Java. So we have as all Java stack as we can get. So I'm on slide 9 now for those who might be listening somewhere else. So there are related work. There is other work in this space, and this is just two of the most well-known ones. BEA, or now Oracle, have had something called LiquidVM for a couple of years now. It's actually a product, and it's their JRocket JVM, as they call it on the bare metal. I believe this started on Xen back in 2006. But now I think their production version runs on VMware. And, so it's out there. What's different about both of these projects and what I'm doing is both of these are traditional C code. So JRocket's written in C. They have a C library that implements network stack and so on. Their Java is as in that left-hand picture is still only up at the top layers. IBM have a thing called Libra, stands for Library Operating System. That's their J9 JVM. Very similar, except Libra, at least at the last count, does this trick of offloading everything to do with network and disk I/O to a sibling guest domain. So it really doesn't do very much in domain. Domain being Xen's word for an active guest operating system. BEA actually have now got all of that stuff in domain, so they have an in-domain network stack and file system access, NFS client, and so on. So let's tell you a little bit. I don't know how much you guys know about Xen. It's an open source hypervisor, originally from Cambridge University, now kind of owned by Citrix, although there's still quite a lot of open source activity. Oracle use it as the base of their VM work. It's distinguished from things like VMware and VirtualBox and the Hyper-V from having this high-level para-virtualization API, which requires the OS to be ported to rather than hosted native. Initially, this was done because it was the easiest way to deal with the fact that the Intel processors of those early days couldn't be virtualized fully because some of the instructions didn't cause traps, and they would just silently fail. So you had to do something in order to get that to work, and VMware rewrites the OS sort of transparently, and Xen said, well, that's too hard. We'll make people port the code, but we'll take advantage of that, and then we'll provide a much better interface. And they certainly did that for I/O. They really have a very convenient and high-level I/O model, which is based on rings that communicate through shared memory. And they have a split device driver model. So in the guest OS, you have a simple front-end driver that typically sends packets or sends disk blocks through to the back end via the ring. And on the back end, you have something that receives that and manages the real device. Now, what is the back end? Well, in Xen world, they have something called the control domain that not only is the place from which you can create new guests and is essentially the sort of the management point, but it also manages real hardware. So that's how you create new domains from within the control domain. The control domain is a fully fledged operating system, either a Linux domain or, in our case, a Solaris domain. There is a trend towards disaggregating and using domains more. There are now hardware device driver domains that are separate from the control domain because they're trying to minimize the amount of software actually in the control domain because it is a security concern how much stuff lives in there. So let's move on to Maxine, this new JVM. This is written in Java, therefore it's meta-circular in the sense that it uses its own facilities to implement itself. Everything in the VM is represented as a Java object. So all the data structures that you access are all represented as Java objects. But there is low-level system programming support. Now, what does that mean? And how is that implemented? JIKES, which is a similar VM from IBM that has been around, has an interface called VM Magic, where special method names are known to the compiler and are compiled specially by the compiler. Maxine uses annotations, which are a feature that came along in Java 5 to annotate methods as being special. And essentially that's an extensible mechanism. You can have all kinds of different annotations to indicate different things. Fundamentally in Maxine, you can look at an object in a variety of different ways. You can see it as an object and use the normal language features for getting at it. You can also look at it as a reference, which is somewhat like an object reference, but you can't say x.y. You actually have to access fields using numeric offsets. References, however, might invoke the use of write barriers for garbage collection if necessary. Below that, there's something called a grip, which is actually a way of seeing below that write barrier. So that when you write the garbage collector in Java, you tend to work with grips. So you're accessing those objects in a different way, and you're bypassing some certain critical operations that would happen in user land. Finally, if you really have to, you can look at an object as a pointer, as an actual machine address, and there are APIs. It all looks, when you see the code for this, it all looks like quite a lot of code is being executed. But because the compiler is aware that these are special methods through the annotations, essentially everything compiles down to the machine code that you would write by hand. So it ends up being efficient. It's just you write it at a higher level of abstraction. A big focus of Maxine is to try and use the tools, particularly the IDEs that application programmers in Java have the benefit of, and bring that to JVM development. So typically we use Eclipse or NetBeans to do the VM development. And that's how you build the system. It's very configurable. You can change the way objects are laid out when you build a VM image. You can change the GC algorithms. You can change the way synchronization is implemented, how the system starts up. All these are done through things called schemes, and you register a scheme which implements an API with the system, and then you provide an implementation of that scheme, and that gets folded into the VM image when it's built. It has a very flexible and extensible optimizing compiler, and unlike most JVMs, it doesn't actually have an interpreter. So rather than starting from an interpreter and then moving to a just-in-time compiler and then finally to an optimizing compiler, Maxine starts with the view that we'll have an optimizing compiler from the beginning, and we'll use a just-in-time compiler to compile additional code, and we won't have an interpreter unless we really need it. We do actually have an interpreter now that was just done by an intern, but it isn't a fundamental part of the system. The system is fundamentally based around the optimizing compiler. And the just-in-time compiler shares a great deal of code with the optimizing compiler. So one feature of existing JVMs is that a typical bytecode will be implemented in 3 different ways. Once in the interpreter, once in the just-in-time compiler, and once again in the optimizing compiler. And they don't really share anything. Whereas in Maxine, we try to write everything just once. So, for example, the way that the JIT implements a bytecode is the method for a bytecode is written in pseudo-Java. Well, it's actually real Java. It just doesn't execute quite that way. So you have something like push an operand, push another one, add, and pop the operand. Those method calls are actually annotated as being special. That gets fed through the compiler to produce bytecodes, which then gets fed through the optimizing compiler to produce machine code for whatever target you're working for. And that produces a template instruction sequence that when you compile the application class file, each bytecode, you just go and look up in a table and find that template and plug it all together into a single instruction stream. So essentially, the JIT is machine independent, which is unusual. The question?
You said, I think I may have misunderstood. You said the optimizer compiler gets triggered first and then the JIT?
Yes. So can I defer that? Because when I talk about how the images are built, you'll understand that.
Okay, that's fine.
Okay.
And you'll have to read if you get questions after reading.
Yes, right. Okay. It's portable in terms of its instruction set architecture, independence, OS dependency, well factored. A key thing is it's fully JD6 compatible. One of the goals is that you can take Hotspot, including the JDK, and drop Maxine right in on top of Hotspot, and the applications will still run. So that's in contrast to JIKES, where they use GNU, ClassPath, and a bunch of other things. Typically, you can't run fully production applications. Maxine is designed to run production apps, and I can verify that. So how do you build one of these images, since this is a somewhat different environment? Essentially, you feed the system through itself, and you compile the entire VM and most of the platform with the optimizing compiler. And what you get out of that is a disk file, which is essentially an image of the VM, with lots of machine code, and also lots of what's called a bootstrap heap, which is a lot of pre-allocated objects that get relocated together. That gets memory mapped at runtime and then relocated by a little C startup program, and then you're up and running. And once you've got started, what the VM does is actually just delegates to this runtime scheme to see what we're going to do. And typically, we're just going to load a main class and run, but we might use this for, say, running test programs. So instead of having some special testing framework, we have a testing run scheme that runs tests that have been compiled into the image. And then after that, any additional classes are loaded in the normal way, and they get compiled initially with a just-in-time compiler and then possibly eventually by the optimizing compiler if they're used enough. So that's how the bytecode thing works there. Right. So it runs on itself, but it runs on itself initially in some other VM like Hotspot to build one of these images. So GuestVM images are similar but a little bit different. There are a bunch of additional classes that you need, for example, file system support. They have to be there up front. You can't dynamically load these because where are you going to dynamically load them from? Well, you're going to load them from a file system. Well, how do you run your file system when you haven't included it in the image? So there's a bootstrap problem, and we have to have some additional stuff. So I exploited the run scheme mechanism of Maxine to come up with an extension mechanism to add new classes, in fact, a variety of different things, to be able to reinitialize things if necessary, to be able to include files in the image, a bunch of things like that. It's a very general mechanism. It's not limited to GuestVM, and it's actually part of the standard Maxine distribution. And I use it in a special way. My images get converted to ELF files, and then they get statically linked with the microkernel. And then when the microkernel starts up after Xen fires it up, we pass into the normal Maxine startup code. And from then on, it's very much the same. So I said that we wanted Maxine to be a drop-in replacement, and the question is, how does this work? Because the Hotspot JDK native code is dependent on Hotspot. There is a connection between those two. Anything in the in the native side of a standard Java platform that needs to depend on VM basics is specific to that VM. We use something called the substitute annotation, and I use this extensively to essentially replace all of the native code for, say, the network API classes with Java code. So if you look at the bottom here, we have a method from java.net, which gets all the network interfaces on your platform. And the way this is implemented in Maxine in general and GuestVM in specific is in one of my packages, I import java.net.star, and I also import my implementation classes. And I say, this class is going to be substituting some methods in the network interface class. And it's now a private final class because I don't want anyone to actually access this thing. It's going to be accessed through the normal public API of java.net, but I name it in this curious way to remind myself of what it actually is. And then this method is now a substitute method. And say, okay, it's the same syntax except it's not native anymore. And I implement it using those ComSun GuestVM net API classes. The way that the optimizing compiler handles this at image build time is whenever it's going to fill in a virtual method slot or a static slot for this particular class is instead of putting in something that would eventually jump to the normal native code, it actually patches in the call to this class, this method, which it discovers, it had better discover that it's in the image build, all right? And of course, if it can't find it, it's going to complain. So it's a kind of overloading mechanism, but it's a little trickier than that. But it turns out to be crucial to be able to have this drop-in trick. Okay, so let's move on to the components of GuestVM. So I talk about the microkernel, a little about the network stack, the file system, and the thread scheduler, which are the most interesting components. So the microkernel, if you download the Xen distribution and you look in extras, you'll find a thing called MiniOS, which is an exemplar guest operating system. It doesn't do very much, but it's supposed to be sort of a hint as to what you might need to do to implement a new guest. This turns out to be very important because the API for Xen is not very well documented. So it's actually useful to go and read this. And it's quite a good starting point. It's being used more actually within the Xen world now for small domains. So we took it and added a lot of new features because it was pretty primitive. It didn't support more than one CPU. It didn't have preemptive threading. Didn't have any debugging support. Didn't have a disk handler. So we added all those things. And we've recently messed with its thread scheduler to go to a 2-level system. So this is now essentially a parallel implementation of this that will, of course, get put back into the distribution because it's GPL and derived from that. So the network stack, this is a fully integrated TCP/IP network stack written in Java, originally developed for Sun's Java Station. I don't know whether any of you remember this remarkable device that Sun, in one of its flights of fancy in the mid-90s, decided we should all have these on our desks, or at least some people should. It was, I believe, a totally interpreted system. It wasn't terribly successful, but the network stack was just fine and got used for a bunch of other things, and it works very well. I've reworked it with a bunch of 1.5 features because this was written in '96. I mean, there's some very, very basic code in here. Just a lot of stuff wasn't available when it was written. So it wasn't multi-threaded in particular. It was a bit of a problem. So that's been changed a little bit. And the network device driver, in some sense, is written in Java. But as I said, the interface to Xen is sufficiently high level that it's not like a typical device driver. We're talking really about Ethernet packets that flow across that ring from the driver domain. So either I'm writing an Ethernet packet or I'm receiving an Ethernet packet. But when an incoming packet comes in, it comes in asynchronously on whatever thread happens to be running and upcalls into Java to deal with the packet we're actually, we really are in interrupt context at that point, and so we can't run fully fledged Java. We can't do synchronized methods. We can't do things that might block. We need to use spin locks and things like that in order to do synchronization. But we hand the packet off essentially and wake up a thread that is waiting for incoming packets, and that's a fully fledged Java thread. That does use, once it's picked up the packets, can use, in fact, the packets at that point become garbage collected objects, and everything there that flows up the stack is 100% Java, nothing special. So that works fine. So we just, right at the lowest level, we have to be a little bit careful about what we do. So file systems. So as I said, everything's network-based in these server apps pretty much, but you still need a file system. I mean, application servers have, they do put some configuration information in files and so on. I mean, they're not doing massive amounts of it, but you need it. It's also, in a development environment, pretty important to have access to files. So what we do, though, is we just implement what the platform needs. So in particular, if you go and look at java.io.star and you go and grep for all the native methods, you essentially find an interface that is specific to that implementation of Java I/O of all the things that you need to do to get I/O to work. So the obvious thing to do is just define effectively a virtual file system interface that mimics those native methods. Then implement it in Java for various different file systems. And I ended up with 5. The one at the bottom is the one I started with, which is one that delegates off to the sibling domain. It goes off and talks to a Linux domain that's running in parallel. What's interesting about it, that's nice about the Xen high-level API, is you can essentially define your own protocol for communicating across the ring to do these kind of inter-domain calls. So, it's like inventing something on top of UDP, except you're inventing it on top of the Xen ring layer. So we have an API that essentially is of the form open file, read bytes, seek, and so on, all the things that you actually need to do. They don't get broken down into something more low level. We just send them off at the highest level. It turned out to be convenient to have a file system that was actually in the image. It's just a hash table, effectively. But it's nice to have stuff there that's right there after you built the image. Of course, we have a temp file system. It's just in the heap. It's different from this one because it's mutable, whereas the one that's in the image is immutable. Once we got the disk driver, which only happened last summer, we needed a real file system. And so I looked around and I found one of these operating systems that's written by the guys who really are on the bare metal. It's called JNode. It comes from the University of Manchester. And they have an ext2 implementation, which is one of Linux, I think, early Linux file system. And so we just took that and tweaked it a little bit, but basically dropped right in, implemented the VFS interface to it, and now we have disk files. And the final piece is the NFS client. This is actually a piece of open source Sun code that was done, again, several years ago in some fit of enthusiasm by somebody, called WebNFS originally. It's now called Yet Another NFS. But again, it works, it dropped right in, and so now we have NFS access from the domain too. So a lot of different file systems. So now it gets a bit more interesting in some ways, thread scheduling. So this is where we can exploit the fact that we can do Java-specific thread scheduling. So there are 2 kinds of threads in the system, and there are 2 schedulers now. But there aren't 2 thread systems. So everything is a kernel thread. It's just who gets to schedule which thread is what is different. So we're not multiplexing, M Java threads onto N kernel threads and those kind of games we used to play with green threads. In the microkernel, there are a bunch of threads that most of which actually are to do with startup and bootstrap, handling network setup, handling some of the rings setup, communicating through XenStore, which I didn't mention, but XenStore is a tree-structured information communication mechanism that is a way you can sort of pass certain things back and forth between domains, such as what's your network device really. Most of these actually terminate after bootstrap, so we don't really need to worry about scheduling them. But we do need to worry about scheduling them initially. And this bootstrap startup is a little complex. And so it was impractical to kind of totally replace it. So what we decided to do instead was go to a two-level scheduler. So the microkernel thread scheduler, which was part of Minios, stays much the same. When it can't find anything to do, it upcalls into Java, the Java thread scheduler. Actually, it's a little bit more, it actually works both ways. You can have the microkernel thread scheduler schedule all the Java threads if you want to. So it's just an option to say, I want upcalls active, and then at that point it'll start firing things up. And so in Java, we've got two kinds of threads. We've got VM threads, things like the garbage collector threads, the compiler thread, and so on. And we've got application threads. And that actually turns out to be important to know that there's a distinction. So the goals we have for this is we want to enable custom scheduling applications, algorithms. My belief is that these server applications, each one is different, and that there may not be a generic scheduler that is optimal for each of them. And that if it's easy enough, you can just customize or write a new scheduler for that particular application. And there's a fair amount of research going on in the community in trying to do this. People who are trying to do things like, instead of having a time slice for a thread, you have a memory allocation slice, right? And you schedule it after, you preempt it after it's allocated a megabyte. And some people have shown that you can get, with certain applications, improved performance that way. So that's what we're trying to do here. Same way that Maxine is trying to encourage JVM research, we're trying to encourage lower-level systems research in Java. But currently people are doing by first hacking hotspot to do this, and then coming up with an interface to Linux so that they can send more information down to Linux scheduler, and then hacking the Linux scheduler to implement this new algorithm. It's not fun, guys. You know, I mean, in this world, this is a lot easier. We're all in. You do all this in Eclipse, and you build one thing, and you run it, and that's the idea. So obviously, we want to keep the policy and the mechanism separate as always, and keep the tricky code constant, because you certainly can shoot yourself in the foot here if you don't get certain key things right. I mean, then nothing works, and that's kind of bad. So basically, the control flow is really this upcall model. At certain key times, the microkernel upcalls to say, you know, I'm scheduling a Java thread, or this thread's blocking, or this thread is waking up, and so on. So the advantages we get from this, well, first thing is it's a simpler problem. I mean, we're trying to, you know, we're essentially scheduling one cooperatively threaded application, whereas the OS scheduler has to deal with the fact that it's got many uncooperative processes. And so the algorithm doesn't need to be, although it might be specialized, it doesn't necessarily need to be as sophisticated as, say, the Linux scheduler, because it's got, in some sense, a simpler problem. We also know which threads are which. So we know something's a GC thread. It probably isn't worth preempting a GC thread in certain circumstances. If it's doing something it really needs to complete, if you're doing a stop world GC, there's no point in preempting that thread. You just want to run it till it's complete, because everyone's blocked until the GC is done anyway. It's nice and easy to add new functions, you know, changing the time slice, making it a thread-specific time slice. That's trivial, straightforward in this world. Disabling preemption for threads is easy, but this meta-circularity can certainly be tricky. You enter the scheduler in the middle of a GC. Who knows what state your object references are in? They may be partially copied. So you've got to be careful. The traditional careful is don't write in Java, write in some lower level, which means perhaps use the lower level features like the grips and don't use object references. So yes, it's not entirely obvious that you certainly can't be just blind and write as if you're an application program at this level, but that's okay. A little bit on debugging. So there's basically nothing in the Xen world for doing inter-guest debugging until very recently. Actually, a guy at Oracle has recently developed some GDB support and some stuff, but when I started this, there was nothing. One of the really nice features of Maxine is it has a GUI-based debugger that understands Maxine JVM data structures. So you can, first it's GUI, and so you see everything in that nice way, and you can click on things, and if they're objects, it'll show you their VM state, and so on. And this was all motivated by a lot of the work that was done in, say, the self environment originally. It uses ptrace or libproc to talk to the target VM. In the Xen world, again, we created another of these pseudo device drivers, another custom protocol to communicate between the debugger and the target domain. And that turned out to be a fairly simple thing to do. We had to put a little bit of support in the microkernel for it, but not much. Here's a picture, which I don't expect you to be able to read, but this is what your typical sort of developer is looking at when they're debugging the VM. Up here we've got the threads and their state, names. We've got registers, so this is low level. Here we've got the stacks. We can see the call stack. We can see various VM notions. Here's the code. This is actually in JITted code. You can tell that by the fact that there are all these colors. Each of these bands of color corresponds to a template, which is a sequence of machine instructions that corresponds to 1 byte code. And over here we've got breakpoints, and this is actually a little object that I clicked on. One of these registers happened to be, if it's in green, then the inspector knows it's an object, and when you click on it, it'll tell you what kind of object it is, and this is a string, even though you can't read that. So this is how I debug most of the VM, how the VM developers work, and this is unique to Maxine. There is nothing equivalent to this in, say, JIKES. Okay. So what is the status and availability of this work? Well, I'm running on Solaris XVM, which is Sun's version of Xen, on AMD 64. We made a decision to be 64-bit only because we don't think that in 3 years' time, when this might be a product, say, that 32-bit will be interesting on the server side, even if it is now. And that, that just simplifies things a little bit. The inspector's fully functional. We've got non-trivial programs executing. The network stack supports all the JavaNet APIs. Big apps, which I'll say more on the next page, are in sort of test and debug mode. Plan to open source it by Java 1 2009, and Maxine already open sourced in 2008. So that's important. So future work, so big apps. So I'm really a person who's interested in, I've done a lot of work with application servers and in the previous projects I worked on, and I'm much more interested in big apps than I am in micro benchmarks. So here's 3. Sun has an application server called Glassfish, which is open source. I've also worked with JBoss. That works fine too. And that's what I consider something worth trying to benchmark. Sun also has a game server now written entirely in Java called Darkstar, which is pretty interesting. And pretty interesting because it has some interesting scheduling behaviors because of the way it's written and the API they present to the game developers. And that, of course, is Hadoop, which I probably don't need to tell any of you about since it's a rip-off of Google's stuff. But it's written in Java, and it's another big app. So all of those things I've experimented with. They've run to a certain degree. Ultimately, and first off, I'm going to compare performance. That's the performance slide I would have if I was further along would be, how does Glassfish running on Maxine on Solaris or Linux compare against Maxine running on GuestVM? Now, I'm not going to compare Hotspot against Maxine because the difference in the compiler quality would dwarf anything else. So it is going to be an apples-to-apples comparison. In the longer term, specialization and optimization, once we've got the thing essentially working, we can start doing the interesting stuff. I mentioned custom thread scheduling already. Memory management, there's potentially some interesting stuff to do there. In the hypervisor environment, you're essentially leveraging overcommitment of everything. And there are people interested in overcommitting memory. It's a little more challenging. But the JVM has some interesting potential. I mean, although you probably wouldn't run a semi-space collector as a production GC, it is the case that when you are, half your memory is unused for that period, and so you could give it back to the hypervisor as long as you get it back when you want to do the copy. And a typical Java app does have fairly aggressive memory requirements, and maybe there is a way, once you know the internals, to be more intelligent about how you manage that. Ultimately, though, we really want to exploit the ability that we now have a stack that goes all the way down, essentially, to the network driver, and that we can optimize the application, the JVM, and the quote OS unquote together with the runtime compiler, do even more analysis than we're doing today with Hotspot and those kinds of VMs, and really make this stack sing. So conclusion today, obviously they're not complete because they don't have performance numbers, but I like Xen's para-virtualization API. I think the device driver model is very convenient and easy to use. Unfortunately, the API is poorly documented. I mean, that's being generous. And I think the reason for this is not much new guest development going on. There aren't people doing what I'm doing. Essentially, it's all Linux, right? One flavor of Linux or another. And so, they just take what's already there and run with it. And you haven't got a lot of people doing brand new guests. So who cares if the API is not documented, right? Maxine has been very powerful and easy to work with and very flexible, but no doubt it takes a long time to get a VM to competitive performance levels. And that's just takes time. As far as GuestVM itself is concerned, I think the fact that I can run things like Glassfish to a certain degree until it falls over with GC bug, I think the proof of concept has been demonstrated that you can sit the platform on top of the hypervisor and it does perform. But what the performance improvement actually is, and we hope it's a positive one, it could turn out to be negative. Could turn out that the OS is so good and those layers don't really matter, but I'm optimistic that in the end they will. But that's to be measured, so we're not quite there yet. And with that, I will throw it open to questions. Or not. To be fair, so the question is, what the people working in the thread scheduling area, what other conclusions they may have reached already to inspire me to do this work. To be fair, right, the papers around that work came out after I started the work. And so it's gratifying to see that people are working in that and they are interested in a platform like this, considering the pain they have today to go through their other stuff. So there was nothing specific. There was just general sense that we can improve the world of platform developer if we do more of it in Java than we do today. Right, so the question is how is this actually controlled? Is it the application developer who's in charge of, say, which thread scheduling algorithm they run and so on? Well, traditionally there are options that directed at the VM to control its behavior that are separate, although the application developer or runner ends up setting those. So the extent to which things can be boiled down to an option that you can control, then that you would continue to follow that. Putting together the application with, I say, a completely custom thread scheduler would be perhaps something that your average application developer isn't going to want to do. But on the other hand, the people developing these big apps like application servers and game servers, they're not average application developers. I don't think they would be, in fact, too concerned about that. In this world, it would be essentially when you build the image, you would specify a particular thread scheduling scheme, and it would be, so it's a parameter at that level to the image build, and then that's it. And so it's so you're alluding to the fact that people have suggested it would be nice to have multiple concurrent GC algorithms active in the same VM, and how on earth do you control that from a management perspective, perhaps, and how would you do that for thread scheduling, too? People have done that. People have suggested that and have done some implementations where you can have the VM switch GC algorithms on the fly. I'm not aware of it being available in any production VMs. One of the people actually who works on this is Tony Prentasis, who's actually at Sun, but he did some research work on this. Ideally your VM is just figures it out, right? If you give it enough tools and enough power and enough and you throw all the algorithms in the final analysis it just gets it right. But of course we're a million miles away from that, and so I've certainly experienced the pain of trying to configure the GC algorithms that exist today, because it's complicated, and you make one slight misstep and your performance is, non-linear effects happen in your performance. So I think it remains a challenge once you've got the power to control it in the right way. Dials, you'd ideally like some dial that you can, rotate and it just gets it right. But in a sense, that's separate from having the ability to put the mechanisms in. So I'm addressing that first, and then how you manage it is, in some sense, a separable question. The thing I alluded to at the beginning is the one thing that's happening here is we're all going to be managing all this at the VM layer, whereas today we might have to manage the scheduler at the OS layer, and we might have to manage the GC at the Java layer. So we're at least putting it into a single management framework, which is a small step, but it's not obviously the final answer. Yes?
So you want Reynolds for more info? Those are Sun internal?
No, they're not. They're actually they are, aren't they? That's good. It should be sunlabs.research.sun.com. Thank you for picking that up.
I had Maxine, but I could not find Guest.
Try Java Guest instead. That means that the request I put into our webmaster to alias that has not actually happened. Yeah. And you won't find too much there yet, because externally it's, we have to be careful, and we're still working through the open source stuff, so more will come. Yeah, Hiroshi. Oh, yeah, okay. About the... Oh. Well, footprint will be one. You are in a smaller footprint. They run WebLogic on top of Liquid VM, and so they have a smaller footprint. In principle, they could get a lot of value out of doing custom thread scheduling. They could also get memory management advantages. So if they have actually done the work inside their C layer to take advantage of those features, then they ought to be getting improvements. When I heard them talk about it last, they hadn't done any of that. They'd simply got it working. I'm sure since it's a product now, they've been beavering away on this and have actually gone somewhere in that direction, but there's no public information about it, so I don't know. But the potential's there. And Sun could get the same with Hotspot. We could put Hotspot on Xen and get the same thing in principle. So what differs, this work is the all Java stack. So the question is, how much code did I have to write before I had the bare minimum thing running on top of Xen? Well, see, Minios is a great starting point, because Minios runs. So it actually will run. What it does is tell you what the time is, and it just keeps doing that. So it's a little thread that tells you the time. So you get there. The first thing I did actually was put the, I don't know whether you've heard of a VM called Squawk. It's the VM that Sun puts in its sunspots, the very, very small devices. And as a way of keeping the VM simple and the Xen part, whereas where I was focusing, I originally ported that. So the very first thing I got running was a Squawk VM, which ran Hello World. But this hypervisor layer is thin, and in particular the little piece that sits on top of Minios that talks, that hooks into the Maxine startup is very, very small. So I had things running pretty quickly, actually. Yeah. Okay. All right. One more question. How does the image file's footprint compare to class files? The image file is quite large for two reasons. One is it's got a lot of not particularly well optimized code in it and a lot of data structures that probably don't really strictly need to be there. We've got some work to do to try and cut the footprint down. So since we're not imagining that we're going to be downloading one of these things, we don't really care about the footprint of the image file, to be honest. It certainly is less than the footprint of the OS plus a hotspot image. So the question is, how much time do we spend relocating the pointers in the image in the boot heap when we start up? I think it's probably vanishingly small compared to almost anything else. I mean, I don't know. It's a linear function of how many pointers there are in the heap. It's really pretty quick. Yeah. So startup time. This is something I sort of wasn't really expecting. But startup time in the Xen environment is really interesting. I sit there at a shell in the control domain, and I run the program with a script that does one of these XM create things, which is the way that Xen creates guests. And it's very, very easy to just forget that you're running on a hypervisor and you're actually forking what is potentially an entire operating system, because it's as fast, almost as fast as running a process in Unix. So it's spiffy. And so, yeah, startup time is great and not a problem. And here's the good thing about big apps that have a long startup time and all the hassles about how long it takes to compile it. You get checkpointing for free in Xen, and we support checkpointing in GuestVM. So you run your application up, you load it up, you load all the classes, you JIT everything, and then you checkpoint it. And then you run it from there, and it starts in 0 time, essentially. So you can forget about that as a problem. And you can migrate it to another machine if you want. So you get a lot of nice things that come along with Xen, essentially for free. Yeah. Okay. All right. I think we're done. Okay. You're welcome.